Okay, so second example here. Example 2 of thin film interference. Here we go. We have a situation we've all encountered at some point in our lives where there's oil on top of water. I remember this most vividly from back in the 70s when I was a kid. You know, cars leaked oil all the time. And so you'd walk out sometimes on the driveway or in the driveway after a rain, and you'd see oil on top of the water puddle. And it would be this nice, pretty little, rainbowy effect, kind of like the soap bubbles, kind of like the soap film in the video you watched earlier. The sun is shining down on it, which is white light. Okay, so the sun, there's the sun. Sun shining on it, white light. Some of that light gets reflected back up, and here we are, the pink disembodied floating eyeball. Looking down at this, some of that light gets reflected immediately up off the oil, which has an index of 1.28. Some of that light refracts down into the oil, and some of that reflects back up off the water, which has a higher index of 1.33. That's why the oil floats. It's less dense, has a lower index, so it floats on top of the water. You've seen this too when you have oil and water in the kitchen or something. You can see it layer out like that. We're going to get a second reflection now off of the water layer, and then we're going to have ray 2. So we have 2 rays entering our eye, combining on our retina, adding up either constructively or destructively. So this is the sun, this is white light. Again, all these angles are very small. So the path length difference delta is 2t, as it's been all along. And we have to answer the question. Well, we know the thickness of the oil, 420 nanometers. And so the question is, what visible color is reflected strongly, and what visible color is not reflected at all. So 2 parts. What color is reflected strongly? That's the color that it looks like. So if you look at a part of the oil and it looks blue, that blue is reflecting strongly. What is not reflected at all? That is, what is completely destructively, what color just completely destructively interferes. So the first question has to do with constructive interference. The second question is a question about destructive interference. With destructive interference, there's no reflection at all, because the light in that wavelength is completely canceled out. It's completely, it interferes with itself completely. So here we have, again, our 2 points. First point of reflection A, second point of reflection B. At A, there is a phase shift, because you're going reflecting off of a material with a higher index than the material you're in, right? You're going low to high, reflecting off a high index of refraction. So, right, 1.28 is bigger than 1.00 in my universe anyway. So there's going to be a phase shift at A. And at B, there's also going to be a phase shift. This is different than the last example with the soap film. This is different than that, because H2O has a higher index than the oil, 1.33 versus 1.28. So there will be a phase shift at B also. So now there are 2 phase shifts. One at A, one at B. Okay, one at A and one at B. Okay. So if you look back at our formulas from earlier, okay, if there are no phase shifts, or if there are 2 phase shifts, then the condition for constructive interference is 2t, 2nt equals m lambda. That is the formula for constructive interference for 0 or 2 phase shifts. Here we have 2. So this is our condition for constructive interference. If there were only 1 phase shift as last time, we would have the 2nt equals m plus 1/2 lambda condition. Okay? So what color is reflected strongly? That's a lambda question. So here's part A. Lambda is 2nt over m. Well, we know 2n and t. We know 2n is 1 point, right? The path length difference occurs in the oil. That's the important one. Path length difference, 2t, down and back for ray 2, occurs within the oil. So this is the index that you use, times 420. Just got that, 420 nanometers. Over what? Well, we can't put 0 there, right? M equals 0 doesn't make any sense. You can't have something over 0. An infinite wavelength, that's silly. So we're going to start with the lowest value of m for this formula. That's m equals 1. And find out what happens. So this is the m equals 1 case. Okay? We're just trying to see which wavelengths fit into the visible part of the spectrum. When you do this, you get 1008 nanometers, which is infrared, not visible. So infrared light might be reflecting from it, but we can't see it. The question was, what visible color? Okay, so not that. Try m equals 2. If you plug in the numbers for m equals 2, you get half this number, which comes out to be 504. Now that is visible. That is green. Okay, nice, calming, natural green. Okay. And if you put in m equals 3, you're going to get something in, I don't know the number, but m equals 3 leads to something in the ultraviolet. So that is the color that is strongly reflected. Okay? So it's going to look green to you. Now let's see if we can put in B down here. Okay. Now our condition is 2nt equals m plus 1/2 lambda. And we're going to do the same thing. Now we have m equals 0 is a possibility, right? Because when m equals 0, this equation still makes sense. This one doesn't, right? The condition for constructive interference doesn't make sense with m equals 0, because then you have 0 thickness, and you don't have a problem, right? If m is 0, then t is 0. But for this condition, m equals 0 does make sense. And so if you plug in m equals 0 and solve for lambda, you get something big. You get something 2016 nanometers, which again is infrared and not visible. If you put in m equals 1, then you're going to get lambda. And you can do this yourself. Plug these in. I just don't have room on the board. If you put in that, you get 672 nanometers. And that is deep red. So that is one wavelength that does not show up because this now is the condition for destructive interference when you have two phase shifts at A and at B. So this is an answer. Let's keep going and see if there's another visible wavelength that does not show up. Put in m equals 2, okay, and you end up getting lambda is 403 nanometers, which is just barely visible. You female students can probably see it. I'm talking to postbacks here as well as undergrads. Because women can generally see deeper shades of purple, shorter wavelengths than men can. This might be invisible to male persons, but this is deep purple, very deep violet. And that will also not show up in the reflected light because it's destructive. And finally, you can't see it here, but if we were to do an m equals 3 case, we would again get UV. So one wavelength of visible light, green, shows up nice and bright in this case. Two wavelengths of light, visible light, are completely destructively interfered with. They completely destructively interfere with themselves, I should say, and you don't see them at all. So green, 504 nanometers is the answer to A, and red and deep violet are two answers to part B. You can't see them. But you need to go in and run through all your M's, and of course, anything outside of the 400 to 700 nanometer window does not work, right? So when I say visible, that means between 400 and 700 nanometers. Anything that falls outside of that is not visible. All right, well, that's it for thin film interference. I'll see y'all next time. Take care.